Swayam Prabha. Digital India. Educated India.
Welcome everyone to our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself, Professor Anjali Pal. We are both from Civil Engineering Department of IIT Kharagpur. We have divided this course into two parts. The first part is environmental chemistry, that will be covered by me, and the second part is environmental microbiology, that will be taught by Professor Sudha Goel. Now, in our module 1, we have discussed about the acids, bases and salts. In module 2, I have discussed about chemical equilibrium, and in the module 3, I discussed about chemical kinetics. I have told about the reaction rate, reaction order, how to determine the reaction order, and also I discussed about the differential rate law and integrated rate law. In this lecture, I will cover the environmental chemical kinetics under environmental chemistry and the mechanism of reactions. This is the part A and it is the lecture 16. Now, the lecture content here is molecularity, elementary reaction, unimolecular reaction, bimolecular reaction, termolecular reaction and chain reaction. You all know that in the general way we show a reaction by a balanced equation, but it is very important to know the mechanism of the reaction, detailed mechanism of the reaction, and to know the detailed mechanism we need to have the idea on these following topics that I mentioned here. Now, what is the molecularity and order? What is the difference between the molecularity and order of a reaction? Molecularity of a chemical reaction, usually we mean that in a balanced equation, the number of molecules that is reacting, that is the molecularity of the reaction. In that sense, the reaction may be unimolecular, where only one molecule is reacting, then it can be bimolecular, where two molecules are reacting, it may be termolecular, where three molecules are reacting, and earlier actually there we did not distinguish between the molecularity and order of a chemical reaction. But now, after the discussion of chemical kinetics in the module 3, you all know that molecularity and order is not the same, and usually to mean the molecularity we apply the term molecularity to explain the mechanism of a chemical reaction, but order, you know, we have no control. It is the experimentally determined parameter, and it can be a fraction also, it can be integer also, but molecularity is always a integral. Now, so we understand that molecularity and order are two different things for a chemical reaction. Now, in case of simple reaction or isolated reaction or elementary reaction, I will tell you about the elementary reaction, but that type of reactions where the reactants are directly transformed into products without any intermediate step, their molecularity can be easily defined. Say for example, it is the simple reaction of hydroiodic acid. This is hydroiodic acid decomposition, where two molecules of hydroiodic acid is producing one molecule of hydrogen and one molecule of iodine. It is very simple here to, and you can easily tell that it is because this is 2. So, you can easily tell that this is a bimolecular reaction. But if you see the opposite reaction, say for example, one molecule of hydrogen is combining with one molecule of iodine, then producing two molecules of HI, then if you see this reaction, then also you can tell that opposite reaction is also a bimolecular reaction. Very simple to understand, and it is directly it is going on, that is why it is simple to understand. But incidentally there are also second order reaction, but it is not necessary that molecularity and the order will be same, it may be different also, that we will discuss in this lecture. Now, what is elementary reaction? This is very important to know for to understand the mechanism of a chemical reaction. What is elementary reaction? It is generally known that most of the reactions do not occur in a single step. We know that we have usually in in our school days, we never bothered about the mechanism of a reaction. We only have shown the balanced equation. But now while talking about the mechanism, we must consider the different steps, various steps, because many of the reaction, most of the reactions, they do not occur in a single step, but occurs through a series of steps, maybe 2 steps, 3 steps, 4 steps, 5 steps. So, each step is called an elementary reaction and is directly caused by the collisions of atoms, ions or molecules. We all know that a reaction cannot occur like that unless there is the collision, and during the collision it has to have a particular threshold energy, that is activation energy. So, in the elementary step, when any elementary step when it occurs, it has to fulfill that condition. Now, the rate expression of an overall reaction cannot be derived from the stoichiometry of the balanced equation. We cannot tell, we cannot find out the order, we cannot write the rate expression just from the stoichiometry of the balanced equation, and must be determined, that is the order, that is the, unless we know the order, we cannot tell the rate expression, we cannot write the rate expression. That is why order is important, and to know the order we have to do the experiment. So, the rate of elementary reaction on the other hand, elementary reaction means each step is called, because one reaction can occur in several steps. So, 2, 3 or 4 or 5 steps. So, each step is called the elementary reaction, and is directly, the rate of elementary reaction on the other hand is directly proportional to the product of the concentrations of the reacting species. That means, in elementary steps it is very easy to find out the molecularity of that particular elementary step. Each raised to a power equal to its coefficient in the balanced elementary equation. So, if we see the elementary equation, balanced elementary equation, then we can easily find out the rate expression for that particular elementary equation. There is no correlation, however, there is no correlation between the order and the molecularity of a reaction, or between the stoichiometric representation and the molecularity. This we must understand. Okay. Usually we think that order is directly, it is the same as the molecularity, but it is not the same. So, once order is not known, then we cannot tell also the rate expression. Okay. Every elementary step has its molecularity, that is what I told you. Every elementary step you can write, you can find out the molecularity by writing the balanced equation. Now, here is an example. What is the example? It is the nitrogen pentoxide. Nitrogen pentoxide, when decomposed, it is producing NO2 and oxygen. It is a, you can see here, it is a balanced equation, and you can see here it is 2, stoichiometry is 2. That means, you can easily tell, you will tell, it is presumed that it is a bimolecular reaction, but actually and also by simple way, if you tell that this is a second order reaction, then you are not correct. Actually, experimentally, when we find out the order, we see it is a first order reaction. The reaction occurs, why it is so, why it is not matching? Because the reaction occurs by multiple steps, some of which are bimolecular and one is unimolecular. So, and all the steps are not occurring in the at equal speed, that is another thing. Someone is slow, someone is fast. So, how to determine the molecularity and how to determine the order? Order it is experimentally determined, that is for sure, but how to tell the molecularity, that is very important thing. And often, although often it is observed that molecularity of the slowest step is the order of the overall reaction. So, slowest step is a very important term to tell about the mechanism of a particular reaction. I will tell you later what does it mean. Now, different types of elementary reaction. If you tell that what is the elementary reaction, it is the slowest step. What does it mean? I will give you some idea. Okay. Say for example, you are going to, say for example, I am going from Kharagpur to Delhi. Okay. So, this is my route. So, I will tell Kharagpur to Delhi, but to go from Kharagpur to Delhi, I cannot go directly there, same as the reaction. Okay. I cannot go directly from Kharagpur to Delhi. What I have to do? First, I have to go to Kharagpur station by taxi or something. Then from Kharagpur station, I have to catch a train to go to Kolkata. Then from Kolkata to airport we have to go, and then from airport I will catch a flight to go to Delhi. Now, say for example, in this journey one step is very slow. Say for example, the Kharagpur to Kolkata, it, say for example, it is a very slow moving train, okay, and then it takes maybe 10 hours to go. Okay. So, and if when you catch the flight to go to Delhi, it takes 1.5 hours. Okay. So, the step which is the slow step, that is nothing but the train, slow moving train, you are going from Kharagpur to Kolkata. Now, if you, so it is altogether it is taking too much time. Okay. Now, if you want to go fast, then which step you have to consider mostly, means you have to you have to pay attention, the slow step. If you want to go fast, the slow step which is taking more time, that step you have to make fast. So, you have to either go by a car or you have to go by a fast moving train, so that it takes only 1 hour time. Okay. And then you can say that okay, I can reach Delhi in a very small time period. Okay. So, that means the slowest step is the governing factor to tell you whether the overall process is fast or slow, and that is the same thing here. Now, I will tell you first what are the different molecularity, based on the molecularity what are the different reactions. Okay. Something like unimolecular reaction. So, what is uni means one, we know. So, unimolecular reaction involves a single reactant molecule and usually occurs after at least one bimolecular step. Why it is written here? After at least one bimolecular step. This is very important, but easy to visualize. Say for example, there is one molecule. So, to go for some reaction, to do some reaction, to take part in the reaction, if it is just one molecule, it will not be involved in some molecular not in reaction. Okay. So, to take part in the reaction, it must collide with some other molecule, maybe same molecule means similar molecule, or it may be a different molecule. Okay. Otherwise, it will not go for reaction. This is very easy to visualize. Okay. So, as say for example, N2O5 again nitrogen pentoxide, but here the reaction is different. N2O5 to produce NO2 and NO3. Okay. So, N2O5 is there which will produce NO2 and NO3, but then if it is a unimolecular reaction, this is not visualized. Okay. Unimolecular reaction to unnecessary, why it will decompose. Okay. To do this decomposition, it must collide with some other species, maybe it is the same molecule or maybe something else, whatever may be. So, when it collides with sufficient energy, then only what will happen to this molecule, it will go to some excited state. Okay. And when it will go to excited state, we know that excited molecules cannot stay there for long time. So, it will in the second step, this is the first step, and in the second step it will the excited molecule, excited, to show the excited molecule we use the star here. So, the excited molecule will decompose into NO2 and NO3. So, what we have seen that unimolecular reaction is following a bimolecular reaction. So, first step is here two things are there, N2O5 and M. So, it is a bimolecular reaction, and then this is a unimolecular reaction. That is why it is written, it involves a single reactant and usually occurs after at least one bimolecular step. This is very important, that I have explained here. Now, if this is the thing happening, the N2O5 molecule is an excited state and high energy. So, it dissociates in the second step. It is clear. So, if it is like this, then rate is what? Rate is the, this is the rate expression, rate is it is the rate constant and N2O5 that. So, it is clear that second step is unimolecular and has the rate expression like this. Okay. So, according to this, if you forget about this, if this is the step unimolecular reaction, if you consider, then what will be the rate expression? Rate expression is K into N2O5, concentration of N2O5. Now, here it is a gas phase reaction. So, it is colliding with another molecule or it may be colliding with something else also. But in liquid solvents, the elementary reaction involve the encounter of solute species with one another. So, in solvent system it is possible that two ions or two molecules or whatever they can encounter. Although the solvent molecule may affect the reaction, sometimes solvent molecule can affect the reaction, but we have learnt that when it is solvent molecule, then it will not come in the rate expression. So, accordingly you have to write the rate expression. Now, bimolecular reaction, it is most common. Bimolecular reaction is most common. We have seen the reaction of HI, decomposition of HI to hydrogen and iodine, or we have seen the reaction of hydrogen and iodine to form the hydroiodic acid. Both are bimolecular reaction. This is very common. Many reactions are bimolecular reactions. Say for example, NO, this is also gas phase reaction, NO with ozone, it is forming NO2 and oxygen. Here it is expected that the rate of collision is proportional to the product of the concentration of NO and O3, because there are two species here. So, it is very simple to write the rate expression, it is nothing but K into concentration of NO into concentration of O3. Molecularity is often used to indicate the number of molecules that take part in the elementary reaction. For elementary reaction, to tell the molecularity is very easy, that much we understand. Okay. Now, the term molecular reactions, term means 3, Intermolecular reaction, it is also not very common. I visualize in this way. Say for example, two people are running in a particular corridor. Okay. So, two people when running, there is enough chance that they will collide with each other. But if there are three people running, it is not very easy to think that at a particular time three of them will come at a particular spot to collide. Okay. That is nothing but the intermolecular reaction. So, that is why it is said that intermolecular reactions are not very common. Okay. So, what is the example? For example, recombination of iodine atoms in gas phase to form iodine molecules. This is the example we have taken. Okay. In this process, a huge amount of energy is released and it causes the iodine molecule to dissociate immediately. So, what is the reaction? Recombination of iodine atom I plus I giving iodine. Okay. This is also a gas phase reaction, iodine I and I giving I2. So, that is also a gas phase reaction, but when it gives iodine, then in this process a huge amount of energy is released and it causes the iodine molecule to dissociate immediately. That means, the reaction will not occur. Okay. I plus I giving I2, this reaction theoretically is possible, but it will not occur because once it is formed, then it releases a huge amount of energy and that energy will cause them to fly apart. That means, reaction will not occur. However, in presence of an inert gas, sufficient high concentration of inert gas, if there is some inert gas present like argon, then what will happen? Then the argon will take out some of the energy, excess energy, okay, and then the recombination is possible. So, argon has taken away some of the excess energy and then what will happen? The reaction now can occur and it is nothing but a intermolecular reaction. See, for example, I plus argon will produce the iodine, and then if this happens, then what should be the rate expression? The rate expression will be K into I to the power square, I concentration to the power square into argon concentration. So, an interesting observation is that the recombination of iodine atoms occur readily in solution. Like it is gas phase reaction and it is shown here that argon is necessary or any inert gas is necessary, so that excess energy will be taken away. But if the reaction is done in some solution, then what will happen? Then this excess energy, this solvent can take out and then the reaction will occur. The reaction is bimolecular and the rate expression is rate is equals to K into K is, this is nothing but the specific rate constant, I concentration to the power square, means I concentration to the power 2. Okay. So, intermolecular reaction is possible, somewhere it is possible, but it is not very common like the bimolecular reaction. Now, chain reaction, this is many environmental segments we see that chain reaction is going on. Okay. So, here what is chain reaction? In the chain reaction, the speciality of chain reaction is that it occurs through various steps. Okay. First step is initiation, then propagation and then termination, and during these steps initiation and propagation, free radicals and which are nothing but intermediates are produced and finally, they will in the termination step they will combine and they will terminate the reaction. So, what is, let us see an example. For example, methane in gas phase reacting with fluorine, that is also gas, and then it is producing CH3F and HF. Okay. All this is a gas phase reaction. Okay. Now, if you means this is very simple things to show or to see, but is it occurring like this in a single step or it is occurring through multiple steps? That is the question, because we are talking about the mechanism of a reaction. Now, although it should be a single step. If it is a single step reaction, then we can tell easily that it is a bimolecular reaction, but actually it occurs through a series of steps such as CH4 plus fluorine. This is the first step, which is called initiation. In the initiation step, you can see that methyl radical is generated and another radical is generated, fluorine dot. So, how the radicals are written? This is the dot, that means free radical, that means it has unpaired electron. Okay. Now, these free radicals are very reactive, and they can react with something else again to form another free radical. Okay. And this way, you see, this is the initiation step. This means initiation of formation by the formation of some free radicals. Then propagation. Propagation means there are many steps where other free radicals are being generated. Okay. These are all propagation step, step 2, step 3. Now, you see that in the step 4, you see the free radicals are recombined, and then it is producing some compound. So, here there is no more free radical left. This way it will go on continuously, and that means continuously producing more and more free radicals, and it takes place continuously in various steps. So, the important thing about it is that the chain reaction between this here methane and fluorine proceeds at a constant rate. And why? Because these propagation steps consume and produce. They produce as well as they consume the intermediates. These free radicals are called intermediates. Okay. And the concentration of the reactive intermediates remain approximately constant. That is why the rate is also constant. Okay. These are determined by the rates of chain initiation and chain termination. You will see this when I will discuss about the radioactivity, then you will see this type of thing is happening for radioactive elements. Their free radical is not generated, but there are some daughter elements are generated, and you will see that radioactive equilibrium. Okay. And so, this is the chain reaction. Now, chain reaction, you know, I told you that in nature also it is happening. It is a very interesting thing that ozone layer, you know, ozone layer, it is present in the stratosphere. Naturally it is produced, okay, in the stratosphere. How naturally it is produced? By this series of reactions, like in the stratosphere there is oxygen, and then high energy photon is coming, and it is breaking it into O and O. You see the such a high energy, it is 200 nanometer from the thermosphere. So, in the thermosphere it is happening. Now, this O is combining with oxygen to form the ozone, and it is happening in stratosphere. Now, ozone, you see, it can means it is excited molecule. You see star. So, star is coming down to the ground state by colliding with something M. M is anything. Okay. So, it is coming to the ground state, and this is the natural formation. So, these 3 steps I have shown the natural formation. Now, this one you forget, it is nothing related to this one, but this is a reaction that happens in lab. Okay. Ozone can form the oxygen, but it is a slow reaction. Now, ozone can react with photon, but you can see here, this is the light of 200 nanometer, this is the light wavelength 200 to 350 nanometer, means higher wavelength. Okay. So, energy is less, okay. Here energy is more. So, what is happening? Ozone forms oxygen and O. Okay. So, natural depletion, this is the natural. So, formation and depletion is going on naturally to maintain this concentration of ozone in the, this is steady state. So, this is the molecules per liter, 10 to the power 15 molecules of ozone per liter, this is maintained. So, this was maintained, and it is protecting us from the UV light. We all know that the ozone layer is a protective layer, it is protecting us from the UV light. Okay. Now, what is happening? Due to some man-made activities, man-made activities, this ozone layer is getting depleted. How it is going on? These are nitrogen oxides, NO, nitric oxide, supersonic jets it is coming, and then it is reacting with ozone to form some intermediates. Here it is not free radical, but it is some intermediate, and that intermediate again is combining with oxygen to form the NO and O2. So, you see the intermediate, you have to find out something, that intermediate final reaction it is not there, but it can go on as a chain reaction, and finally, you see ozone is decomposed to oxygen. So, this is the man-made activity that is going on. Another man-made activity is that chlorofluorocarbon. You know, from the refrigerators, from many sprays, chlorofluorocarbon is coming, and then it is reacting with photon, normal light, and then it is producing the free radical, chlorine free radical, and this free radical can destroy the ozone through a series of chain reactions. Okay, series of reactions which is nothing but chain reaction, we have just learned. So, this is the reason that ozone layer is depleted, and it is making ozone holes in many places, and then it is the UV light is coming to the earth, and it is creating lot of hazard for our health. Okay. That is why it is so important, and the mechanism of ozone layer depletion was first described by 3 scientists, and Nobel Prize 1995 Nobel Prize was given for this, for the understanding of the mechanism of ozone layer depletion. So, this is in the nature it is happening, and this is nothing but the chain reaction. Similarly, we also tell that photochemical smog formation. We know that in the industrial areas brown haze is formed, which irritates our eyes, and it creates breathing problem. That is also like a cyclic chain type of chain reaction, and it is producing NO2, several types of nitrogen gases, NOx, and it is a very dangerous thing. So, there also if you go through that photochemical smog formation, then you will see that these type of reactions, chain reactions are going on. So, the references that I have written here, you can have all those things that I discussed, you can see it in a more elaborative way. So, you can read these 3 books. There are 3 books written here, process chemistry and water for water and wastewater treatment, that I have already mentioned in my earlier lectures, and this is a book, very nice book, and P.K. Datta, and that. So, you can read these 3 books. Now, this is the conclusion. So, in this lecture what we have covered? We have discussed about the molecularity and elementary process. We have also explained that what is unimolecular reaction, bimolecular reaction, termomolecular reaction, and also chain reaction that have been discussed here in this lecture. Okay, thank you very much.